greetings to the panel as well as Dr. Rasha. Dr. Rasha and Professor Adela. So I'd like to talk about my topic for my research, which is the real-time traffic protection using neural network model to reduce traffic congestion in Malaysia. So my name is Yong Yi, and my metric number is 240714446. Course is WQD 7025 Data Science Research Project. So compared to previously, right now using this data source, we have managed to streamline from a much complex one to a more cost-effective data set. So this can be done by synchronizing the data set into one single data set. So previously there was two separate GitHub repository. So there was limitation in the budget. So there's only up to $25 a month of runtime, which is not really feasible, as well as the API was limitation to $200 per month. So yeah, much to effect, I've decided that it's better to just maintain one repository. So this unified collection repository was the solution to synchronize and enrich the data. So this phase of the project, because we combined two data sets and also I decided to enrich the data, I expanded from 26 to 33 classes and also added a validation attribute called data pass to ensure that all data sequence actually pass so that we can filter on in the next stage, including cleaning. Yeah, that sometimes where it could fail and be not detected in the dataset, which is a problem. Yeah, so we'll show this later more in the demonstration. Okay, so for the network that the system that I've been using on the camera feeds to detect the vehicles using the you only look once version 11. So it's a much upgraded version from the version 5. This version 11 actually has pixel level masking and also more granular. And it's much more accurate to detect objects in complex traffic scene. So across this, you can see a deck of camera feeds. So you can apply a pixel level mask into the vehicle, and therefore knowing what's the vehicle concentration. So vehicle concentration, I'll be streamlining it to high, heavy, medium, or low, which I will later also show in the demonstration. And yeah, so these are some of the examples, the scenario that we can is expected. So okay, this is actually the feature selection. So feature selection, we're using Weka, and Weka is Hokkaido framework is developed by researchers in the University of Hokkaido. So using this, I could gain analysis into which features are more attributed to the East Gen. So the purpose of this is to make sure that when we are training, we make sure the features are closely interlinked to the East Gen classification, and is those loosely run towards the East Gen will be eliminated, or it's probably not impacting the scores later. So you can see that the top trend would be, of course, the journey time. Journey time is actually hand in hand with this jam. So longer journey time obviously will mean heavier jam. Would mean there's a jam. Type of day, of course, this is the single predictor that shows the highest at 0.072868. And then we have type of day coming at second. Then LG2 is actually a gate diagram. So this is leaving gate 2. And then this is peak hour. Then it's entering gate 2. So then the timestamp, date, day name, LG3, destination coordinate, so on and so forth. So what does this actually mean? So meaning that calculate generates a stronger signal for predicting jam. When strong signals such as type of day and its peak hour and timestamp are highly influential for temporal features. And there's also weather attributes. So weather attributes also can contribute to our data sets. We will see that later. So of course I have origin windy, origin raining, showing whether the location is actually raining or windy. And of course there's also flags for holidays, meaning whether it's effective like Christmas or the school holiday. Yeah. Okay, let's put moving on. So here we see a comparison between the base model and also three other models. So the base model, obviously, right now, we will only select which would perform the best. So the initial performance right now we've seen was the preliminary performance. Okay, the preliminary performance we've seen that random forest is actually quite high in accuracy at 92.61%. Then for logistic regression, however, has also decent accuracy at 90.95, LSTM 90.02, and KNN at 19.61. So all above the 90%. I think this is better than compared before the P1 results. So I'm actually quite conclusive and satisfied with the results, showing that actually with this newer data sets, we actually get to have better insights, more encoded. Okay, so yeah, so there is this, and so random forest has high accuracy, and you see were compelling, but the R2 score were very low, and the false positive rate is 35%, which is quite high of C. So that is why we also would consider LSTM and also logistic regression. Obviously, we need to use LSTM because it's our neural network. So, okay. Now we have already compared LSTM on model level. Now we compare on layer level. On layer level, we will see that standard deep classifier actually is a better layer compared to three other layers that I've also engineered. So the layers that I've engineered actually is stack LSTM, bottleneck LP, and also deep regressive. So this is actually how the layers actually sequence. So dense layer has activation of value, and then we also have the loss function. Yeah, so pretty much this is the architecture of the layer. Yeah. And yeah, so this also I will show in a demonstration of how that the architecture is inputted into Weka, and then we will get the results from there. It might take some time because we're also running cross-validation 10. So yeah, I think I've not mentioned this before yet, but as a baseline, we will use cross-validation 10 for this layer. So okay. Then we have the dashboard. Obviously, the dashboard is actually very intuitive, and it's real-time for monitoring, and also it's able to give personals like security and also security personals or traffic wardens on decision making. So yeah, I will show this in the demonstration as well. So what about beneficial about this dashboard is it shows 6 days predictive forecast, 30-minute intervals, and it shows a live map feed containing the JSPEC checkpoints, which is we have the FSKTM and also all the gates. Then we also show the model performance. So we also can compare preloaded onboard model performance. And that's for a general visualization and guide for users who just utilize the dashboard. So, okay, overall, this pipeline is to ensure that when we collect the data, the model the data and dashboard will update with the minimum intervention. So for this entire system to work, we start from the data ingestion all the way to final visualization. It's going to be very robust. So it's tested and this workflow is actually working. So from the start, we have the configuration and ingestion. So yes, we have the data source from OpenMeteor and also Google API, and then also from the images that we collect from the Highway Authority of Malaysia, which is processed by the Python script, which is this, the traffic collector.py. And at automation level and storage level, we have the traffic schedule. And this traffic schedule is actually workflow, so it will run every 30 minutes. Post that we have seen that you export traffic data CSV. So this is like an on cloud storage at GitHub. And then from there we can extract the data to Weka. And with Weka, we can do modeling analysis. So we can do feature selection, model experimentation, before finally we can deploy and monitor. So when we deploy and monitor, we have the index HTML script. So this is connecting to the GitHub pages. Then we have a live prediction dashboard. So this LSTM network proofs is very good for Malaysian traffic prediction for a smart city, right? So we're moving towards that. And with this deep learning, we combine with meticulous data engineering and model optimization, we can improve traffic forecast. So this project actually will both validate a model and practical tool on real-world application. So these key highlights of this project is evaluated separately. So the optimized deep classifier understands the path to random forest, achieving a 2.7 accuracy with 38% lower false positive rate. And it showcases a holistic framework. It develops an end-to-end automated pipeline from live data capture to an interactive user dashboard. It showcases a real-world impact. So to meet as part of the nation's and also institution effort to meet the SDG goals, this project meets the SDG 3 and SDG 11, which is the good health and well-being and also the sustainable cities. So also I will gather the feedback from the students, and I've seen most of them agree that the UI UX is also great. So for future directions, then we have the GRU model, which is the gated recurrent unit, which is much more simpler, and then we have the bidirectional model, and also the refined hyperparameters. Without further ado, let me just jump straight into Weka. So yes, this is Weka. We'll use Explorer. And yeah, so I've actually run this for the results. And the first one was actually I programmed for the standard deep classifier, then the deep regressor, then the stack LSTM, and finally the backend bottleneck MLP. So we have when we load on the data set, we go to this side, and we have open file, open file, then select traffic normal CSV. I've loaded this, and we can see the attribute inside. Of course, we have HGen, which shows the imbalance data. There is no need to balance the data, although I could do it from the interface, but I think it's not necessary because we don't need to. It's not really a major issue. So once we have done that, we will just run. So let's say I would just program a deep LSTM layer. So what I do is I right click, then I will show properties, and then all this will leave it at the default setting. So here we can choose the layer. So for example, if I were to set a layer for the first approach on the standard deep classifier, we need dense layer. So add 2 dense layer and then 1 output layer. So of course I can configure the dense layer to settings that we just now discussed. Configure them. Yeah, so the bottleneck, back to the bottleneck MLP, actually what I did was actually I just squeeze the data, squeezing it. Then after that, coming out, you will see that the data has been forced to retrain on a type layer and then expanded into a bigger layer. So I think this one is 32 because the number of classes. Okay, and then we close this. Okay, we can hit run. So all this running, we can just go and look at the dashboard. So I've actually prepared my dashboard. Okay. So from the dashboard, we have the charts. Yeah, we have today, yesterday, 2 days ago, 3 days ago, tomorrow, and the after. The red section indicates the predicted. The blue section will indicate the historical data. So all these are actually reported correctly. Then we also, yeah, so that one was 28 routes. Then we have CTVs. Right, you can see the traffic feed. It's yeah, it's all. It's currently at this time, it's 2 o'clock in the morning. Yeah, so I think there's nothing much to see, which is why our charts did not we did not want to run to exceed the runtime as well. So yeah, we have also the weather radar with the wind radar. Then we have of course, the preloaded CV10 80/20 speed for four models, LSTM, random forest, logistic regression, and K nearest neighbor. And we have the metrics from accuracy, AP rate, position, recall, F1 score, EUC, MAE, everything else back. So the traffic data we'll see. Okay, I not probably use this one, but since this is downloaded, we have we have all this jam. Yeah, pretty much we can see everything. It's quite dense, but works. So all the way to today, today is 4th January, and you can see my data. I mean, sorry, you can see my data for up to 9:30, yeah, which is yesterday. Okay, I think that's about it for this data. Let's go back to Weka. Okay, it's still running. So I think one of the few questions that we always tackle in traffic prediction is when I did my project was how to perform a critical analysis on limitation current models. So I believe this was actually we made a critical analysis using the LSTM layers, and we also compared with the traditional models. So yes, that was one of the objectives. As well, another objective is develop a base model traffic prediction using neural network, KNN random forest. Of course, that is also completed in a model. And also to evaluate the impact of traffic prediction growth to high traffic urban areas in Malaysia. So specifically, we've chosen a visiting layer for a specific reason because it is much more simplicity and uh, much more directed compared to choosing a random location in KL, because it would probably make more correlate with the student and correlate with us. And eventually you can phase out to use in the broader city of KL. So that has been run. I think the results has been out, and yeah, you can see, yes, it's about that. Mhm. You got the results for the LSTM layer for the standard bit classifier. Yeah, so sorry, that was under C5. To run CV10 but it will take longer. And yeah, so that's the end of my presentation, and I hope this would answer your queries, and I look forward to hearing from you. So thank you so much.